2.7 Polynomial and Rational Inequalities. So our objective for this section is to solve polynomial inequalities and to solve rational inequalities, and then to solve some word problems modeled by polynomial or rational inequalities. So in the last couple sections, we've sort of built up a way to figure out the zeros of polynomial functions using synthetic division and by analyzing their graphs in section 2.3 and 2.4 and 2.5. In 2.6, last section, we talked about graphing rational functions and what their graph looked like. So now we're going to use all that information and solve polynomial inequalities. Okay, and this is going to be a little bit different. Okay, so the definition of a polynomial inequality is basically the same as any other inequality, right? We're going to have some sort of inequality symbol, less than, greater than, less than or equal to, or greater than or equal to 0, greater than or equal always to 0, and we're going to try to figure out where this is true for each function. So to solve polynomial inequalities, graphs usually can help visualize the solutions of polynomial inequalities. For example, the graph of f of x is equal to x squared minus 7x plus 10 in the picture. You can see that it has two x-intercepts, 2 and 5. These are also called the boundary points between where the graph lies above the x-axis, right, in the blue, and below the x-axis in the maroon, okay, and or red, right? So when you look at this graph, clearly this part of the graph is negative, this part of the graph is positive, okay? This part is less than 0, this part is greater than 0. Okay, so we have a 5-step procedure to solve polynomial inequalities. The first is probably the most important. Put it in the form of 0 on the right-hand side. So we're going to say f of x is less than 0 or greater than 0 or less than or equal to or greater than or equal to. Always set it with 0 on the right-hand side. Solve the equation f of x is equal to 0. So pretend that these two symbols were a 0 and solve this. However, you have to do it. If it's a quadratic, like our first example, those are usually pretty easy to solve. If it's a upper degree, then we're going to need to use our techniques that we learned from section 2.5, which is to guess possible zeros using the rational zero theorem, use synthetic division and see which one works, and then factor accordingly. So once you solve these equations, you've now find the real zeros, and these are the boundary points. If you think of any polynomial function, right? So here's our graph. Any polynomial function, if I find these 3 points, I know those zeros are where the graph is going to change from a positive to a negative or from a negative to a positive. Nowhere else, which is what's nice about polynomial functions. When we talk about rational functions, that's not necessarily true. Okay, but for a polynomial function, the graph can only change from being above the x-axis or below the x-axis at one of those boundary points. So what we can do once we, in step 3, locate the boundary points on a number line, thereby dividing the number line into intervals. So we are going to make sort of like we're going to make a sign chart. Okay, and what we're going to do is we're going to just make a number line. We're going to put these 3 points on that number line, and then we're going to pick a number in between it and evaluate the function. Okay, so that's called a test value. So choose a representative number called a test value within each interval and evaluate f at that number. If the value of f is positive, then f of x greater than 0 for all numbers x in the interval. Okay. If the value of f is negative, then f of x is always going to be less than 0 for all numbers on that interval. Okay, so that basically says that once you pick one value, once you pick one test value, you know what's happening on an interval. So say I say if I use this little graph I just made, if I took 0 and plugged it into this function, I would get a positive number, which means that all the answers in between those two boundary points are going to be positive. Also, I could use what I know about polynomial graphs and behaviors and multiple zeros to just look at the polynomial and figure out what the signs are going to be. So I'll show you both methods. Okay? And then finally, 5, write a solution set selecting the interval or intervals that satisfy the given inequality. Okay? And like I said at the beginning, this procedure is valid if less than is replaced by less than or equal to. Okay? Just remember to use the correct signs in interval notation, either parentheses or brackets. So here we go. Solve and graph the solution set for 2x squared plus x greater than 15. So, step 1. We are going to express the inequality with 0 on the right-hand side. So basically all I do is subtract 15 from both sides, and I get 2x squared plus x minus 15 is greater than 0. Nice and easy. Okay? Step 2. Solve the equation f of x is equal to 0. So we're going to solve this. Okay, well, I could try to use the quadratic formula if I have to, but I don't because this actually factors, right? So I have the factors of 2, which are 1 and 2, factors of 15, 1 and 15, 3 and 5, and I see that if I multiply 2 times 3 and 1 times 5, subtract those answers, I get 1. So my factors become 2x and x there, and then I want the 3 over there, the 5 there, a minus and a plus, FOIL those together, and I see that it does work. So x is going to be equal to 5 over 2 and negative 3. Okay? So step 3 is to make a number line. So make our nice little number line. I'm going to put a negative 3 on there. I'm going to put a 5 over 2. Okay? Now, when I look at these 3 points, or when I look at these 3 intervals, I have to decide, is this equation positive or negative in each of these sections? Well, probably the easiest thing to do for step 4, choose a test value. So step 4, let's try f of 0, which is right in there. So if I plug 0 into this function, either my function right here or my function over here, if I plug 0 into this function, it says negative, well, let's do, so let's, it says f of 0 would give me, that would be, say, 0 is greater than 15. If I plug it into my original equation, or if I plug it in over here, it would say negative 15 is greater than 0. Neither one of those is true, okay? So, actually, better idea is to just plug f of 0 and see what you get, a positive or negative number. Plug it into your equation right here, and we get f of 0 is equal to negative 15. So that means that this function is negative in the interval for 0. Okay? Now I could plug in negative 4 into this equation right here, and I will get 13, which is a positive. And I could plug in something like, well, this is 2.5, so I could plug in positive 3. If I plug 3 in there, I would get 6, which is also positive. I could have also realized that this is a parabola that opens up, which means the two ends go up because it is even and this exponent is even, the number in front is positive, which means my two ends have to go up. These two zeros happen one time, which means that the graph goes through the boundary point and doesn't repeat. And so I have my nice little sign chart. Now, the question, we're not done yet. We got to write the solution set. So the solution set is, I want to know where this function is positive, greater than 0. So I can see that it's positive in 2 places. So my answer becomes from negative infinity to negative 3 union 5/2 to infinity. And that is my answer. Okay, let's try that again. So set it with 0 on the right-hand side. So we change this to x squared minus x minus 20 is greater than 0. I can factor this. It factors into x minus 5. X plus 4 is greater than 0. So that means x is equal to 5 and x is equal to negative 4. So on my number line, I put in a negative 4. I put in a 5. Usually what I just do is plug in 0 into my function. So f of 0 would be 0 squared minus 0 minus 20, which gives me a negative 20. So 0 is negative, and because the leading coefficient is positive and squared, we know that the two ends go up. Okay, and if you don't like the method of using the end behavior, you could of course plug in negative 5 and plug in something like positive 6 into your function right here and see whether it is positive or negative. Okay, so my answer, I have to see what do I actually want. I want the place where this function is positive. So my answer is from negative infinity to negative 4 union 5 to infinity. And notice I'm using parentheses because it says greater than. If it was greater than or equal to, then I would use brackets. Okay? Let's look at another one. Same situation. Okay? So we have 4x squared plus 2x minus 1 is greater than or equal to, is less than or equal to 0. Okay, so I could try to factor this, but unfortunately, it doesn't factor. Okay, so I'm going to have to use the quadratic formula. So we know that a is equal to 4, b is equal to 2, c is equal to negative 1. So we get that my two zeros are negative b plus or minus the square root of b squared minus 4 times a times c. So that's going to be a plus 16 all over 8. So that's negative 2 plus or minus the square root of 20 over 8. Simplifying that is negative 2 plus or minus 2 square root 5 over 8. And finally, simplifying that gives me negative 1 plus or minus the square root of 5 over 4. Okay? So those are my x-intercepts, and there are 2 of them. Okay? So if we look at my boundary line, all right, we have my first 0, negative 1 minus radical 5 over 4, which is a negative number. And we have this one, negative 1 plus radical 5 over 4. Now, these numbers are kind of complicated. You could easily work it out. This one's about negative 0.8. This one's about negative 0.3. Or sorry, positive 0.3. Okay. But you don't even have to. You know that one is negative, one is positive. Figure out this. Find f of 0. So that turns into 4 times 0 squared plus 2 times 0 minus 1. That's a negative number. which means these two sides are positive from what I know about end behavior in a polynomial function. So I want to know where this graph is negative or equal to 0. So the answer to this, with a bracket, it's only negative here. With a bracket, because it says or equal to, this function would be negative 1 minus radical 5 over 4, comma, negative 1 plus radical 5 over 4. So in between those two is the only places that this graph is negative. And if you wanted to use a graphing utility, you could actually figure that out too. Okay. Let's try another one. Again, here's the start. 2x squared plus 6x plus 1 is less than or equal to 0. I try to factor. It doesn't factor, which means I have to use the quadratic formula. So that would give me a is 2, b is 6, c is positive 1. We have that x is equal to negative b plus or minus the square root of 36 minus 8 all over 4. Okay. 36. That gives me negative 6 plus or minus 2 radical 7 over 4. And I can simplify this to give me negative 3 plus or minus radical 7 over 2. Okay, so on my number line, I have negative 3 minus radical 7 over 2, and I have negative 3 plus radical 7 over 2. Since radical 7 is 2.6, both of these numbers are negative. So negative 3 plus the square root of 7 divided by 2 is going to be negative 0.17. Okay, that's kind of important because now when I plug in f of 0 and I get 1, that's this side. Okay, so that's the only thing you have to be careful with these radical expressions, is make sure you know what the number you're plugging in, where it is going to go on your number line. Okay, and because each of these zeros happens one time, this graph will change signs at each 0. Okay, so to figure out where this graph is negative, it is negative there, which means the answer is going to be nice and ugly. Negative 3 minus radical 7 over 2, all the way until negative 3 plus radical 7 over 2. Okay, so that's our basic procedure, is solve the equation, find the zeros, make a sign chart, figure out where the graph is positive or negative. Okay, so now we have a cubic. Same thing, x to the third plus x squared minus 4x plus 4 is less than or equal to 0. Well, luckily, this one actually factors. Okay, and how do I know it factors? Because I know it does. All right, factor it by grouping. So you can factor out an x squared there. We're left with x plus 1. You could factor out a negative 4 here, and you're left with, we factor it, yeah, little mistake there. Boom. Right, when I move the 4 over the other side, negative 4. So now we have x plus 1 less than or equal to 0. So I now have x squared minus 4 times x plus 1. And of course, x squared minus 4 factors one more time into x plus 2, x minus 2 times x plus 1. So that means my zeros become negative 2, positive 2, negative 1. So now when I make my number line and I'm going to make my sign chart, I put a negative 2, a -1, and a 2 there. Okay? Let's find f of 0. So that turns into 0 to the third plus 0 squared minus 4 times 0, which all just cancel out, minus 4. So 0 is negative. Now again, I could plug in a number in between 1 and 2, like -1.5, plug in a number bigger than 2, plug in a number less than -2. But I know because each one of these zeros happens one time, the graph changes signs at every 0. And I could double check this because my leading coefficient is positive, my exponent is odd, the graph goes down on the left, up on the right, down on the left, up on the right. Okay, so the answer to this question is everywhere that this graph is negative. It is negative there and there. So it is negative from -infinity to -2. Ooh, less than or equal to, which means you need a bracket, union -1 to +2. And that is my answer. Okay? So whether or not you want to use test values or whether or not you want to use the rules of polynomials, which I think is easier, either way, you're going to have to come up with this chart to tell you what the answer is. Let's look at another one. First step, x to the third plus 3x squared minus x minus 3 is less than or equal to 0. I look at that pattern there, and I'm pretty sure that is going to factor with grouping again. So I can factor out an x squared there. I'm left with x plus 3. I can factor out a -1 there, and we're left with x plus 3. And now I have x squared minus 1 times x plus 3. Factors again into x plus 1, x minus 1, x plus 3. And so x is going to equal -1, 1, and -3. Make a sign chart, and we have -3. Always put them in order, of course, because then it's not a real number line anymore. I'm going to plug in 0, which is going to go right. Actually, I don't even have to do that because I can just use, I like to plug in 0 just to make sure a little bit, but I can just use the rules of polynomials and behavior to know that this term, the leading coefficient, is positive. The degree is odd, which means I'm going to start going down, and because each 0 happens only once, the polynomial will change signs at every 0. Each 0 has a multiplicity of 1. So I have my sign chart. I didn't even need to do anything fancy. If I did plug in 0, I would get -3, which means that it is negative in there, which means I did this right. If I wanted to plug in other numbers, I could. I don't have to, though. And I'm looking for the places where this function is less than 0, which is going to be that region and that region. So my answer becomes from -infinity to -3 with a bracket because it's or equal to union -1 to 1. Okay? Now, they could get a little more complicated, right? Both of these factored, which were pretty nice. I didn't include one here in the examples that didn't factor, but if it doesn't factor with grouping, then you're going to need to use the rational zero theorem, which means we take all the factors of 3 divided by all the factors of 1, positive and negative, and we see, right, so that's the possible zeros are going to be plus or minus 1, plus or minus 3, and notice they're all there, okay? And then we would use synthetic division to get this to a quadratic, and once we got it to a quadratic, then we would factor the quadratic. Okay? maybe we'll look at one at the end that doesn't factor. So, rationals. So rationals are slightly different, okay? So a rational inequality is the same thing as an inequality that can be put into one of these forms, less than, greater than, less than or equal to, greater than or equal to. So it's the same idea where f is any rational function, all right? So an example of a rational inequality is just this, right? Function over a function, greater than or greater than 0 instead of equal, okay? So when we look at this rational function, there's a couple things that happens. We can find the x-intercept by setting the numerator equal to 0. And when I do that, I get -1. Okay, so I can see that's an x-intercept of this graph. Okay, but that's not the only way that a rational function could change from positive to negative. You can see on the graph that it also can change at a vertical asymptote, because before the vertical asymptote, the graph is going up, and to the right of the vertical asymptote, the graph is going down. So the limit as x approaches -2 from the left-hand side is positive infinity, and the limit as x approaches -2 from the right-hand side is negative infinity. So the graph does switch signs at intercepts, but it can also switch signs at asymptotes. And unfortunately, there's not such a nice rule as there is with polynomials, where you can just say, oh, it's positive here, and it's just going to jump to negative. That's not always true. Okay, so you're going to have to actually pick a number in between these 2 points and test your function. Okay, so we can figure out where this vertical asymptote is by setting the denominator equal to 0 to give us -2. Okay. So let's solve this. The first step is always going to be the same. Okay? This looks like, well, I could just figure out where it's greater than 2, but that's very hard to do. So we want to make sure we're going to use our same 5-step process. We're going to express the inequality so that one side is a 0 and the other side is 1 quotient. So we're going to start like this. But that's not a rational function, okay? We must express it as 1 quotient, which means we have to put those two things together, which means that we need a common denominator of x plus 3. So I'm going to have to multiply this by x plus 3 over x plus 3 greater than or equal to 0. And so now I have x plus 1 minus 2x minus 6 all over x plus 3. Combine like terms, we get -x minus 5 over x plus 3. Now I have combined this into a nice rational function. That was step 1. Okay. Step 2, we are going to find the boundary points by setting the numerator and the denominator equal to 0 to find the intercepts and the vertical asymptotes, the 2 places where it's possible for this function to cross the x-axis. So we go -x minus 5, we set that equal to 0, and x plus 3, we set that equal to 0. Here we get that x is equal to -5. Here we get -3. Okay, so I make a graph and I put on it -5 and -3. Now, I'm going to start with 0 just because I like to do that. So f of 0 gives me, well, -0 is just 0 minus 5 over 0 plus 3. I don't necessarily care about the answer, which is going to be a fraction. All I really care about is whether that answer is positive or negative. So it's going to be a negative, which means that this region right here is going to be a negative. Okay, well, luckily, this particular function has a nice number to plug in here, so I can just plug in f of -4, which gives me -4, which is 4, minus 5 over negative 4 plus 3. So plugging in negative 4 gives me negative 1 over negative 1, which is positive. Okay. Now, I could say, well, this has to be negative, but it doesn't really have to be, so I do want to check. So let's plug in f of negative 6. And when I do that, I get negative 1/3, so this is negative, yes. Okay, but don't just assume that. So my answer is where this is positive, greater than or equal to 0. So my answer is negative 5 to negative 3, both with brackets. Okay? Oh, sorry, that's not correct. Because that's a vertical asymptote, which means this function cannot actually be equal to negative 3. So we need a parenthesis. Okay? So that's an easy place to make a mistake because you see or equal to, but the function cannot actually be equal to negative 3. So there's my answer. Let's try another one. Okay? So first step. So we have 2x over x plus 1. Subtract 1 from both sides. Okay, we're going to have to put these together. So that's 2x over x plus 1 minus 1 times x plus 1 is my common denominator. Okay, so we get 2x minus x minus 1 over x plus 1. And we have x minus 1 over x plus 1 is greater than or equal to 0. So x equals 1 is my 0. And x equals negative 1 is my vertical asymptote. Okay, so now I make my number line. I know this graph can change signs at these 2 points. So I'm going to need to plug in some things. So let's plug in f of negative 2, f of 0, and f of 2. Figure out all of these, plugging them into my function. So that becomes negative 2 minus 1 over negative 2 plus 1. That's negative 3 over negative 2, which is positive. F of 0 is going to be negative 1 over positive 1, which is negative. And f of 2 becomes 2 minus 1 over 2 plus 1, which is 3 over, 1 over 3, which is positive again. So to figure out where this graph is positive, my answer is there and there. But remember that this one is a vertical asymptote. That one is a vertical asymptote. So that means the graph cannot be equal to negative, or the function cannot actually be equal to negative 1. So my answer is negative infinity to negative 1 with a parenthesis, union with a bracket 1 to positive infinity. Okay. So, how can you use this with some fun word problems? So if you throw an object directly upwards, although its path looks straight and vertical, its changing height over time can be described by a quadratic function. So position function for a free-falling object near the Earth's surface is given by this equation right here. An object that is falling vertically or projected into the air has a height above the ground, s of t, in feet, given by s of t is equal to negative 16t squared plus v sub 0 t plus s sub 0, where v sub 0 is original velocity, or initial velocity, in feet per second. T is time that the object is in motion in seconds, and s sub 0 is the original height, initial height. Maybe you remember this from physics. Okay, so let's try one. Okay, so a ball is thrown vertically upwards from the top of the Leaning Tower of Pisa, 190 feet high, with an initial velocity of 96 feet per second, during which time will the ball's height exceed that of the tower. So if you think about this as the 0 point, we can actually make this function. So we want that s of t for my original function is going to be negative 16t squared plus, well, initial velocity, so that's 96t, plus height, initial height, 190. Okay, so I want to know when this function is going to be greater than the height of the tower. Okay, so that's pretty easy, right? Because what do? First, set 0 on the right-hand side, make it a 0. So subtract 190 from both sides. So negative 16t squared plus 96t is greater than 0. Well, that factors very nicely into negative 16t times t minus 6, which then, when I set it equal to 0, t is equal to 0 for the first one, t is equal to 6 for the second one. So on my little sign chart here, 0 and 6. And because this is obviously a parabola right there, right? If you throw the ball upwards, it's going to start both sides. Well, look, my initial coefficient, my leading coefficient is negative, so both sides go down, which they do. This side, if you kept going, would go down. This side right here goes down, which means that it is only, which you can see from the picture, it's only above the top of the tower from 0 to 6 seconds. So we would write that as, and it is greater than, so my answer would be from 0 to 6. Okay? So a little shorter of a section. Now you should have enough to work on Math Excel 2.7.